All right, well, let's go ahead and get started. So thanks for participating today. I'm Matt Dean with A+ College Ready. This session is being recorded. It'll be uploaded to our A+ College Ready Science YouTube channel. You can go directly there if you want to watch it, or you can ask your teacher for a direct link. Either one will work. If you haven't already muted your microphone and turned off your camera, I'd appreciate it if you did that. That just makes the bandwidth lower and it makes it work with less problems. If you have a question, feel free to turn back on your microphone and ask. The PowerPoints that I'm using, any files that I'm using, I will send to the teachers later today. If you'd like a copy, just email your teacher. First thing I want to do is talk about the exam. There's been some announcements since the last one of these webinars, and we want to talk about the changes that have been made. So for AP Physics 1, the exam date is May 18th. The exam will be completed completely online at your home. According to the College Board, you can use a phone, a tablet, a laptop, or a desktop. Any should work. You're essentially going to have two options. One is to type your answers, which may be hard to do with physics. The other is to write your answers out on paper, take a picture, and upload the pictures. Either option is fine. There's only going to be two questions, and they'll both be free response questions. The first type of question is going to be the qualitative, quantitative reasoning question. We're going to look at an example of what this looks like in a minute. I also sent several examples to teachers today, so they can send you some more examples as well. But you'll have 25 minutes to answer that question. And then after that, you're finished with that question, you'll have 5 additional minutes to upload your answer. When that period of time is up, you'll get question 2. It's going to be what they call a paragraph style question. This question, you'll have 15 minutes to answer, and then another 5 minutes to upload your answer. So essentially from start to finish, you've got 50 minutes. Let's look at an example of what the question 1 type, the qualitative, quantitative reasoning question is going to look like. This is actually a question we looked at in our last session or the session before that. Let me see if I can get that pulled up real quick. So this is a qualitative, quantitative reasoning question. So take a minute and read it. If you've been on our webinars, you've seen this question before. I'll scroll down so you can see parts B, C, D, and so on here in a second. But take a minute and look at that one. And then I'll scroll down as you read. All right, I saw someone said they can't hear. If you cannot hear, please put a message in the chat room. Two things I want to mention about this question. Notice it's 4 parts. I would assume that'll be what you'll see on the AP exam. And they're asking really for 2 things. Let me get to a PowerPoint so I can write better here. So qualitative means to describe a process in terms of words. Here we're not using numbers. We're not using equations. We're talking about words. So if I go back to that question for just a second, notice in part B, they want you to talk about the student's reasoning. What was right? What was not right? That's the qualitative part of the question. And then if you go down and look at part C, use quantitative reasoning. So that's numerical reasoning including equations and variables. That's what they want you to talk about in C. And then D is a little of both put together. So these questions, they're going to be parts that are probably fairly difficult, but there are going to be parts that are really, really easy. For example, like part B. Part A is not bad. You're just having to do a graph. And even part C, you ought to be able to get some points. I'm sorry, part D. Part C might be the harder part, but it's still very doable if you're good with your physics. But my point being, there are going to be some hard parts, but you've got to make sure that you put on paper the answers to the parts you know. Because really, if you get half of the credit, you're probably doing really, really, really good. Let's go ahead and look at the second kind of question. This is the paragraph style question. Here's an example of a paragraph style question. And again, I'll scroll down so you can see more of it in a minute, but go ahead and read what you can see here. And then we'll scroll down and see the rest of it momentarily. So as you can see, there's usually a couple of short answer pieces. Sometimes they're involving graphs. Like in part A, you had to do a free body diagram. In part B, you had to do a sketch of a graph. And then eventually you're going to get to part C, where it says in a clear, coherent paragraph length response, explain why the spheres reach the ground at the same time, even though they travel different distances. And then they want you to refer back to either the data or the chart. So those are your two question types. Again, both types are probably going to have some difficult pieces that you might not be able to answer. But both parts are also going to have some easy parts, some points that are not difficult to come by. You've got to get those points. Take your time, answer what you know. Don't stress too much about the parts you don't know. If you do that, you're going to do fine on this exam. Questions about the exam or the format before we move on with the schedule for today? Anybody have questions about the exam before we move on? All right, well, moving on then. So last time we left off talking about momentum. And we talked about two main ideas when we're dealing with the momentum unit. Let me go to a place where I have some space to write. Really, the two big ideas in the momentum unit are, number one, the law of conservation of momentum. That in a closed system, momentum is conserved, either during collisions or explosions. So essentially the idea there is the momentum before is equal to the momentum after. And momentum, remember, is mass times velocity. So you might have the momentum of object 1 times its original speed, plus the mass of object 2 times its original speed. And that's equal to the momentum after, which would be the momentum of mass 1. It's got some new velocity. We'll say that's v1 prime, plus object 2. It's got some new velocity, v2 prime. Now, these problems are easy to work as long as you're given all the variables except for 1. We're going to talk in a minute what happens if you have 2 unknowns, and we'll talk about how to solve those problems. But idea number one, big idea number one is momentum is conserved in closed systems. Momentum before equals momentum after. Number two idea is the idea of impulses cause change in momentum. Remember, an impulse is a force applied over time. So F delta T causes a momentum change, and a change in momentum is M times change in velocity. If you remember, this equation is really just another way of writing F equals ma, and we can get to that by dividing both sides by delta T. If we do that, you can see F equals M delta V over delta T, and you guys know that change in velocity over change in time is acceleration. But again, two big ideas. Law of conservation of momentum, momentum before equals momentum after, and impulses cause changes in momentum. F delta T equals M delta V. All right, so let's talk about, we also talked, before I go further, we talked about two kinds of collisions. We talked about elastic collisions. These tend to be when two objects bounce off of each other, they collide and bounce off. And in an elastic collision, both momentum is conserved and kinetic energy is conserved. We also talked about inelastic collisions. And in inelastic collisions, momentum's conserved. It's always conserved in a closed system, but kinetic energy is not. So during inelastic collisions, some of that kinetic energy is converted. It's converted to either maybe sound energy or thermal energy, heat. Whereas in an elastic collision, the kinetic energy before is equal to the kinetic energy after. All right, so let's talk about an equation, a problem that has two unknowns. So let's say you have an elastic collision. You have two objects that collide. You know the initial velocity of both of the objects. So let's look at this kind of equation right here. So let's say here's mass A, and let's say we know the mass of mass A, and we know the velocity of A to begin with. Here's mass B. Let's say we know its mass and we know its velocity. So we know the momentum before side. But let's say on the momentum after side, we don't know either of the velocities. We don't know VA prime. We don't know VB prime. So that might be a little bit difficult to solve. But since this is an elastic collision, we know that both momentum and kinetic energy are solved, or conserved rather. Kinetic energy, remember, is 1/2 mv squared. So what I've done in this next equation, or what the textbook did here, is we set up an equation for the kinetic energy of each object. So this is the kinetic energy of object A before the collision. Kinetic energy of object B before the collision. Kinetic energy of object A after the collision. And kinetic energy of object B after the collision. So we have two equations and two unknowns. So what we did next is we rearranged the equations just a bit. So to get this equation, I took the kinetic energy equation and essentially moved this piece over to this side and this piece over to this side. I subtracted 1/2 ma v prime va prime squared, subtracted it over to this side, and then I subtracted 1/2 mb vb squared from both sides and moved it over here. Then I factored out a 1/2 from both sides, canceled those out. Pulled the masses out front. Sorry, that's this top one is the momentum equation. This one is the kinetic energy equation, but it works the same way. Now notice it says, and we'll just read what it says here on the textbook, noting that algebraically a minus b times a plus b equals a squared minus b squared. So we're going to do a little substitution, come up with this equation. And finally, after canceling out some things, derive it down to this equation. Now, what the AP folks tell us in AP Physics 1, you should not have to combine two equations this way. So I doubt you would ever see a problem like this on the exam. But I do want you to think about this equation here, and just in case you need it, it's easy to remember that the velocity of the object before the collision plus the velocity of the same object after the collision is equal to the velocity of the second object before the collision plus the velocity of the second object after the collision. So that'd be a good thing to remember. Let's look at how it might work with the problem. So take a minute and read this problem. Note that it's an elastic collision, meaning that both momentum and kinetic energy are conserved. So again, we're trying to find the velocities of two objects, mass 1 and mass 2. I'm going to go to a slide here where I already have the solution worked out. So first of all, we're going to set up the law of conservation of momentum. Mass 1 times velocity 1 plus mass 2 times velocity 2. And this is the before side. That's equal to mass 1 times v1 prime plus mass 2 times v2 prime. So this is the after side. Going to go ahead and substitute in what I know. So the velocity of object 1 was just v. So now I have m times v plus, well, the mass of v2 was 4m. So I substituted that in for m2. And the velocity of object 2 before the collision was 0. So this is my before the collision. Well, that's equal to the momentum after the collision. Don't know much after the collision. The mass of mass 1 is just m times its velocity. The mass of mass 2 is 4 times m times its velocity. So that's essentially my law of conservation of momentum equation. I still have two unknowns. So now I'm going to solve for v1, or I could solve for v2. Doesn't matter. But if I take this equation right here and solve it out for v1, here's what I get. I'm going to take that, what I solved for there for v1, and I'm going to plug it in to this equation that we just derived. So I'm going to plug in for v1 prime rather. So I end up with v1, which is just the velocity, v, plus v1 prime, which is v minus 4 v2 prime, equals 0 plus v2 prime. So now if I do a little bit of a rearranging here, I get v plus v, so 2v minus 4 v2 prime equals v2 prime. So I can add I can add 4 v2 prime to both sides to get 2v equals 5 v2 prime. Divide both sides by 5 and get v2 prime equals 2/5 of a v. Then if I'm looking for v1, which I need to know the velocity of both, I can take this 2v over 5 and substitute that in here, plug it in right there for v2 prime, solve for v1 prime, and get negative 3/5 v. So lots of steps there. And again, I doubt you're going to see a problem like this on the AP exam because there's taking two equations, merging them together, manipulating. But I just wanted to show you just in case. What I really want to look at today, though, are two FRQs. So let me get to the first of those FRQs. Here's where we're going to start. So take a minute and read FRQ 2 for me, please. All right, so let's pay attention to what we've got here. There's some important ideas to keep in mind here. Notice on part A, sketch the speed of the center of mass. They don't want us to sketch the speed of each block. Sketch the speed of the center of mass. Remember, the center of mass, the velocity of the center of mass and the momentum of the center of mass of a closed system are constant. Notice that what they're defining here as the system is just the two blocks, which means the plunger is not part of the system. Also, the frictional force here, not part of the system. So when those two objects are acting, the force of the plunger and the force of friction, the speed of the center of mass is going to change because those are not parts of the center of mass. So what we want to do here, first of all, is sketch the speed. And let's see, it wants to sketch this as a function of time from TA until TF. So let's think about that. So at TA, we're going to start off down here with 0 speed. We let the plunger start to go. And from, it says that at B, it loses contact with the plunger. So what that means is all the way from A to B, there's a outside positive net force acting on block 1. Well, that outside net force is going to accelerate block 1, which is also going to accelerate the speed of the center of mass. So between points A and B, there's a constant force, therefore a constant acceleration of the velocity of the center of mass. We don't know how high it's going to go. We don't know how fast, but what we need to sketch is between A and B, some kind of upward sloping line, like so maybe. That's showing us that the speed is increasing over time, and we've got a straight diagonal line, which means it's a constant rate because of a constant force. Now, between B and C, there's no external force, which should tell you that the velocity of the center of mass and the momentum of the center of mass stays the same, doesn't change. So between B and C, we need something like this. Then between C and D, we hit the frictional force. The frictional force is not part of our system. So that's an external net force. It's acting opposite of motion, so it's acting to the left. So it's going to decrease the speed of our center of mass. It's a constant force, so it's going to do that in a linear kind of way. So between C and D, our speed is going to decrease. Again, we don't know how much decrease, but the important thing to show is just a nice straight diagonal line, maybe something like that. And then from D all the way to F, we're just on smooth, flat surface, no friction, which means there's no external forces acting. That should tell you that the speed of the center of mass, the momentum of the center of mass should stay constant from D all the way through F. So we'll show that just with a straight horizontal line. So that's what we're looking for on part A. Just a straight graph. Remember that the velocity of the center of mass stays constant unless there's an external net force acting on the object. Any questions on the graph there? So here were the scoring guidelines. So you could have earned, it looks like, up to 4 possible points on part A. You got a point for a straight line that begins at 0 and increases all the way up to B. You got a point for a horizontal non-zero segment between B and C, like that. So 1 point for this segment, 1 point for this segment. You got another point for a segment that decreases linearly from C to D. Another point for that one. And another point for a horizontal non-zero segment between D and F, like so. There are also some ways to get a point if you did a curve, but I think that's probably not necessary at this point. I would say these 4 points are the ones most of you probably could have earned. All right, let's go ahead and look at the second part of this question. Take a minute and read part B. All right, so some keys to decode in this question. Look at the very the next to last sentence, this one right here. In which intervals, if any, does the sphere's angular momentum about its center of mass change? So we're looking for a change in angular momentum. That's L is angular momentum. If you remember, angular momentum is equal to the moment of inertia times the angular velocity. So if you're going to get a change in angular momentum, you're not going to be able to change this because that's determined by the shape and size of the ball. What you are going to be able to change is the velocity, the angular velocity. So you've got to think about what can change angular velocity. And the things that change angular velocity, just like the things that change velocity in a linear kind of setup, are net forces. The thing that's sort of like a net force when we're talking about rotation is a torque. So when there's a change in angular velocity, it's caused by a torque. So you've got to think during which one of these situations do you have an external torque. So notice this says the sphere is pushed by the plunger from A to B with a constant force directed toward the center. So that force is directed toward the center of mass. That's not going to be an external torque. So from A to B, no torque. From B to C, it's just moving across a completely frictionless surface. There's no external force. Therefore, there can't be any external torque. So again, B to C, no torque. But once it hits C to D, there's a force of friction acting between the point of contact and the surface. And that friction's acting this way. So think of this as the radius of the ball. And friction's acting, we could think of it almost as a 90-degree angle. At that point, that's applying a torque. So between C and D, there's a torque acting on this object. There's an external force, the force of friction. That force of friction is acting essentially at a 90-degree angle to the radius, and it's causing It's causing a change in angular velocity. Now from D to E, again, we're on a flat surface, no friction, so there's no torque here either, which means there's no change in angular velocity. So your answer here is between C to D. That's what you're going to check. And you're going to say that that's the only interval where there's an outside net force, which causes an outside external net torque. If we look at the grading rubric on that one, here's what we're looking at on part D. So 1 point for essentially saying that change in angular momentums are caused by net external torques. And then 2, for realizing that net external torque is friction. So 2 possible points. You could answer this whole question in 1-2 sentences tops. We got one more FRQ we're going to look at. So today may be a little bit shorter than our other sessions. Here's FRQ 3. Take a minute and read number 3. All right, so if you've ever played with any kind of collision carts or smart carts, you know that a lot of those carts have magnets in the front, and that if you put those two carts near each other, depending on the way they're turned, either you can get an attractive force or a repulsive force. So here the two carts are facing each other so that they will repel each other. We let them go. What you've got to realize is that the two carts and the magnets, which are part of it, the force of the magnetism, those are part of the system. It's part of the closed system. The track, though, is not quite horizontal. The right side is lower than the left side. So if we think of the system as the two carts, in this case, there's going to be a net external force, and it's the force that's pushing the carts this way. So we'll come back to that in a second. But let's look at the graph. So we're getting graphs here of the momentum versus time for the two carts. So the 5 kilogram cart, notice it is moving with a positive velocity, which means it's going to be moving to the right. And the smaller cart is going to be moving with a negative velocity or negative momentum to the left. So let's look at the first part of the question. So based on the graph, were the measurements started at the instant the carts were released? Justify your answer. That justify, always a big thing in AP questions. Explain, tell why. So first of all, based on the graph, were the measurements started at the instant the carts were released? Let's go back to the graph. What I'm hoping that you're seeing and that you're paying attention to is look right here. Both of those carts at time 0, both of them had momentum. This one is moving. It's got some momentum. This one is moving. It's got some momentum, which means when we started the timer, they were already moving. So if let's go back to the question, were the measurements started at the instant the carts are released? Well, the answer that's got to be no. And we know that because both carts had non-zero momentum at time 0. And that's really all you need to say. So based on the graph where the measurements started at the instant the carts are released, no. And the justification, Both carts had non-zero momentum at t equals 0. That right there would get you all the points. Let's go to the scoring guidelines and look for a second. So here's part A. So just 1 point for saying no. And again, talking about t equals 0. No, the carts had non-zero momentum at t equals 0. Now, this is part B right here. Let's go ahead and look at part B. Calculate the magnitude of the external force exerted on the system. We talked about how there's two big ideas in first of all, the external force is due to the force of gravity because we had that slanted track. I talked about two big ideas in the momentum chapter. Momentum is conserved in a closed system. And I talked about the idea of F delta T equals M delta V. Impulses cause change in momentum. This is the idea we're going to use to work this problem. First of all, I want to go back to the graph, and I want to figure out what's the momentum to begin with. What's the momentum at the beginning of the problem for our system? So if we look right here, this first object, the 5 kilogram object, looks like it has about 0.25 kilogram meters per second of momentum. And then the other object maybe has, let's see, what's a third of 0.5? So like 0.16 or something like that, 0.17. So somewhere about 0.15, 0.16, somewhere like that. Let's just make it easy. Let's just say 0.15 up here. And what we got to remember is this is a negative momentum, which means the momentum at the beginning of my problem is 0.10. That's the beginning momentum. Now let's go over to the end. This one it looks like about 1.25 right here. And then this one has maybe negative 0.6. So if we add those together, that gives us positive 0.65. So this is the momentum after. This is the momentum before. Well, remember, a change in momentum, change in anything, is final minus initial. So 0.65 minus 0.10, our change in momentum is 0.55. That change in momentum is caused by an impulse. So to actually get our answer here, we can say F delta T equals M delta V. We're trying to find the force here. So let's go let's divide both sides by delta T and get F equals M delta V over delta T. Well, remember, this is just the change in momentum. M times delta V is a change in momentum. So we could also write that as delta P over delta T. So F equals delta P over delta T. Our change in momentum was 0.55. And that happened over 10 seconds. So divide that out. And our force ends up being 5.5 newtons. Somewhere in that neighborhood. So let's go to the grading rubric and look and see what they did there. Oh, wait a minute, I did something wrong there. Instead of 5.5, I'm dividing, so my math was wrong. We had 0.55 divided by 10, so it should be 0.055. Sorry about that. 0.55 divided by 10. Here's the grading rubric. So it looks like 4 possible points here. For recognizing the momentum of the system is the sum of the momentum of the 2 carts. 1 point for that. For obtaining reasonable values of momentum from the graph and using them to calculate the system momentum. So calculate the momentum before, calculate the momentum after. 1 point for doing both of those. Another point for calculating the change in momentum. And then finally, the last point for using F delta T equals M delta V, or F equals delta P over T to calculate the force. Notice they got 0.057. I got 0.055. They're going to give you quite a bit of wiggle room in your numbers for rounding. All right, let's go back and look at the last part. So part C says, suppose the experiment is repeated with different carts, so that the masses of each of cart plus magnet are 2 kilograms and 1 kilogram. Now, if you remember, we started with carts that were 1 and 5. This is what we started with. Now we've got 2 different carts, 2 and 4. Would your answer to part B be different with the new masses? So remember, in part B, we were calculating the external force. What I'm hoping that you see is that we started with a system mass of 6, 1 plus 5. In the second version of this lab, we have 2 kilograms plus 4 kilograms, still 6. So constant system mass. Because the system mass is constant, that I hope is telling you that the change in velocity, the force, is going to be constant. The acceleration is going to be constant. So let's look at our rubric. 2 possible points. 1 for saying that it doesn't change. The masses don't change the answer because the calculations in part B account for the effect of the external force. All we did was change the arrangement of the masses. There's a constant system mass, therefore a constant force, a constant acceleration. Not going to change. So that's it for FRQ3, and I think that's it for our momentum FRQ session for today. Before